Right, so far we're doing tight estimates of finite time stability for model systems up to, well, the other thing is you can only talk about probabilistic stability over a finite time, because if you take a system with Gaussian noise, eventually it's going to always leave some region. So we look at finite time stability. Okay, so here's just an example. Take that quadrotor model, add some wind gusts to it, so here's and now it's being buffeted by wind. And we ask the question, if I were to draw some region like this, in 6 dimensions, then can I bound the probability of leaving that region subject to this wind gust model? And so we ran this optimization, took about 5 minutes for 8 states on our computer, and it gives bounds that I'm pretty happy with. So for instance, we can say if you were to let that thing run for an hour, this is a slice from the 8-dimensional stochastic basis. It says, for instance, if I were to start with the initial condition at 0, the probability of leaving is 0.2 over an hour. Now, how do you judge if that's tight? For lower dimensional things, we've done Monte Carlo evaluations to check tightness, but for me, to see that we thought about this thing over an hour time course, and it wasn't 0, and it wasn't 1, that made me very happy, because these are diffusion processes. You either get you either blow up very fast, or you don't blow up very fast. So getting a 0.2 after an hour was an exciting result for us. So the whole theme of this is that I think that the efficient verification leads to better control design. I didn't really care about Lyapunov functions until I convinced myself that that's better controllers. Proving the thing's stable, that's good, but only if it makes controllers work better. So in the stochastic case, it's sort of clear that doing it in a closed form way can be much faster than Monte Carlo and gives good bounds. So maybe that gives us new possibilities for control synthesis. So you can now explicitly optimize the controllers or even the vision systems to try to maximize regions of attraction. And you can start building, by virtue of making the trees and the combinations of funnels, you can make better controllers. Okay, so that's the basic story. Let me just sort of tell you what I think are the weaknesses. Okay, so the biggest weakness I think is that it's a very model-based approach, right? So we spent a long time doing sysid. That's the other thing I didn't want to have to spend as much time on, right? So the better our model, the tighter our bounds, the less robust analysis we have to do, the tighter our bounds, the higher performance our controller could be. We're tracking state space trajectories. It's good state estimation. Another thing I didn't want to spend a lot of time on. It makes sense. I mean, you shouldn't expect to do very high performance things without a model, I think, but it's a burden. And in general, I think control of underactuated systems are very model dependent, because if I don't have an actuator co-located with a joint, I can't just squash nonlinear friction terms and stuff. I have to worry about